Good afternoon, everyone. Welcome back to the mini course, Monotone Operator and Splitting Method. This is the 5th class. In the last class, we have introduced the approximate point method. The first method of multipliers. It's an application of the approximate point method to the door problems. And then we introduced three kinds of approximate point method, and we will begin with recalling what we have discussed last class. First, it's the approximate point method, which is xk plus 1 equals to the resolvent of A at xk, which is I identity plus lambda A inverse xk, which is solving this inclusion problems. Okay. Usually this operator is maximal monotone. This method converges because this resolvent we have discussed before is firmly non-expansive. So the whole iteration converge, and the fixed point of the resolvent is the zero or the solution side of this inclusion problems. Okay, by the definition of this resolvent, we can rewrite these problems or this equality as an inclusion. So we can it is equivalent to say xk belongs to the I plus the lambda A. The input is xk plus 1. And this is also equivalent to say 0 belongs to the lambda A xk plus 1 minus or plus xk plus 1 minus xk. Okay, so the approximate point method is equivalent to solve this inclusion. And if we define a vector vk plus 1, which belongs to A xk plus 1, then we can rewrite this inclusion as this system, which has two steps. First is we want to find vk plus 1 belongs to A xk plus 1. And the second step, because here A is already a vector which belongs to lambda A xk plus 1. So we can use equality instead equality instead of this inclusion. So we have lambda vk plus 1 plus xk plus 1 minus xk equals 0. So this is what we called about the proximal system. It's equivalent to the exact proximal point method. Okay, so we can begin. Next we analyze the arrows. First arrow is by the Rockefeller in his paper in 1970s. He proposed that if we solve this step inexactly, which means the xk plus 1 minus the I plus lambda A inverse xk is not equal 0. If it is equal 0, then you solve this proximal step exactly. So we will permit some arrows here, beta k, in each steps or in each iteration, okay? And if this arrow beta k is summable, if this beta k is summable, then these algorithms converge. This is by Rockefeller. And actually, we have discussed before, this error criteria is not actionable because we want to evaluate this term, okay? This term is somehow we want to approximate, so you cannot use it directly. So we have another one also from the Rockefeller's paper. It's the distance of 0, the lambda, the operator is axk plus 1 plus xk plus 1, and minus xk is less than beta k, and we also require the beta k is summable. Okay, obviously this error criteria is at least actionable, because at least if you have xk plus 1, you already got what is exactly this point. You can take the evaluation of the operator at this point. So this is more actionable than this one. But the problem is this error is summable. So somehow when the k is very large, you almost solve this this proximate step or proximate sub-problem exactly. So this is what we do not like. And in 1999, Zweiter proposed another two kind of error criteria. The first error criteria comes here. We go back to this proximal system, okay? If this is 0, if here it's 0, which means we solve this including exactly, which is equivalent to this ppm. But if we assume we have arrow here, okay? If we have the residue rk here, okay? If we assume the residue rk here, and based on this system, we can write this this absolute error criteria is equivalent to rk. The norm of rk is less than beta k, and the beta k is still summable. Okay, but if we give if we want to construct a more error criteria which you can apply in the real application or in the real algorithms, Zweiter proposed that if the rk, norm of rk, is less than some parameter sigma times the maximum of vk or lambda times the norm yk minus xk. Okay, xk. Okay, let's recall this a little bit. This is much better. This is better than the absolute error, because here we do not need to guarantee that this term approaches 0 when k becomes very large. It just means the rk over vk sorry, there is some. Here should be xk plus 1 minus xk. And here is vk plus 1. Vk plus 1. Rk minus lambda xk plus 1 minus xk. This relative error proposed by Zweiter, which guarantees these two terms is bounded. These two terms is bounded. Actually, this kind of error criteria is analysis based on the interpretation that proximate point method is a kind of projective method. Okay, we have analysis last class, which means if here is a solution site of the inclusion problems, and you have a point xk here, you find a pair vk and xk. Somehow, if the xk plus 1 is here, then we can find a hyperplane which separating the solution site and the point xk. Okay, here is the xk, and this is what we call h or hk. And the direction of vk plus 1 is somehow forward to the solution site. This is the vk plus 1. Okay, and we can interpret these relative arrows based on this. Based on that, the proximate point method is a kind of projective method. Okay, but if we put this proximate system together with these relative arrows, I will write it here. Okay, so first we find a point vk plus 1 belongs to the a xk plus 1, then we have a equation lambda vk plus 1 plus xk plus 1 minus xk equals to rk, and we have the error criteria. The error criteria is the rk is less than sigma maximum of vk plus 1 and the lambda xk plus 1 minus xk. Okay. If we only solve this system with these relative arrows, then the sequence xk, you cannot guarantee it converge to some solution x star. Okay, we cannot guarantee it. So that's why we need another steps here. Sorry, I need this. In the first paper by Solodov and Binar, they propose this kind of hybrid projective proximate method. This is the first step to solve this system with relative arrows, and the second step is the next point xk plus 1 equals to the projection to hk xk, and the hk is determined by the vector vk, and xk is x belongs to Rn, such that the inner product of vk x minus xk plus 1 equals 0. Okay, and we have analysis in the last class. This hyperplane separately the solution site and the point xk. Okay, so we have analysis. These algorithms converge, and next is what we call the HPE, which is called a hybrid approximate extra gradient method. Okay, it's also based on this system. It also has two steps. The first step is also to solve this system, but with a difference. The difference is here. For this hybrid projective proximate point method, the error, or we only have a residue in this system, the operator, evaluation of the operator is exact. But in the HPE, we, instead of solving this including exactly, we permit arrows there. Somehow we say the vk plus 1 belongs to the a epsilon and xk plus 1. Okay, and this a epsilon is the enlargement of this maximal monotone operator. Okay, so what is a monotone? monotone means, okay, if A is monotone means u minus v y minus x is greater than 0 for any u v any u y u and for any x v belongs to the graph of the operator A. Okay, this is monotone. So the enlargement of the maximum monotone operator first means instead of greater than 0, we make the set bigger, so it's greater than the minus epsilon. So if we use the minus epsilon instead of the 0, we consequently immediately we will have a conclusion that the operator A will belong, or the graph of operator A will belong to the graph of the A epsilon enlargement. Okay, so somehow if we use the enlargement here in this inclusion, somehow we enlarge, or no, not enlarge, we permit the arrows here. Okay, so this is the first, in the first step for the inclusion, we permit the arrows in the operator, maximum monotone operator. And the second step is the same, vk plus 1 lambda vk plus 1 plus xk plus 1 minus xk equals to rk, the residual. Okay, but the relative arrow criteria is a little different. Here, because you have in this method, in this hybrid projective proximal method, the arrow only comes here. So the arrow criteria only concern about this step. But here we have two resources of arrows. The first is from the operator, second is from this system. So we assume that rk square plus 2 times the lambda times some constant epsilon is less than the sigma square, it's the arrow parameter xk plus 1 minus xk square. So this is the first step of HPE. 2 point, arrows in the operator, arrows in the system. Okay, the arrows in the system. And then we have a relative arrow criteria. One question is, if we solve this system, guarantee or satisfying this criteria, will the xk converge to some solution x star? The answer is no. We need another step. Like in the first algorithm, we use the projection step. We need somehow another step to guarantee the convergence. Here, the proximal already appears in the first step, okay, because it's a proximal system. Then we need to use this extra gradient, okay. E means extra gradient. Actually, this extra gradient comes from the extra gradient method, or some people call it the Kopelevich method. It was first proposed to solve the variational inequality, and we can take a look at this method, okay, and see how does it works. Okay, this is the extra gradient method. I think this is extra gradient method. It has 2 steps for solving the variational inequality. First step is we take the x here and minus alpha, the operator f, and then we take the projection to yk. Second step is instead of using xk here, we use yk, okay? We use yk, and it's very similar. But let's go to this graph. So what is the meaning of the first step? Why do we need this yk here instead of using the forward method directly? This yk is a direction which can guarantee the point xk or somehow xk plus 1 get closer to the solution site. So in the second step of the extra gradient method, in the first step, we generated the, sorry, there is a typo here. Here should not be yk plus 1, it should be yk. The first step, we generated a good direction yk. And then in the second step, we use this good direction, which means the yk, and which can towards the solution site, okay? The projection here just guarantees the feasibility. Okay, so this is somehow the extra gradient. The idea here in the HPE is the same. In the first step, which we solve this system, this proximal system with two arrows, it gives us somehow a vector vk plus 1. Okay, this vk plus 1. This vk is similar to this, the vk here. Here is a geometric interpretation of ppm, okay? ppm, as I said before, you can interpret it as a projection method. In the exact ppm, these two vectors, xk plus 1 minus xk and vk plus 1, they are parallel, but with the inverse directions. But if the arrow exists in the HPE, we may generate a not exact vk plus 1. Somehow a vk plus 1 like this. We can call it vk plus 1, v bar k plus 1. And this vector is no longer parallel. It's not parallel to the xk plus 1 minus xk anymore. But it can still somehow have or generate a hyperplane, okay? Generate a hyperplane which can separate xk and the solution side. This is exactly the idea in the first algorithm, in this algorithm. That's why we can still use the project to a hyperplane here. But instead of using the projection, we can use the extra gradient step, which means from the last point xk, we know vk plus 1 is a good direction. So we can minus somehow lambda vk plus 1. So this is what we call the extra gradient step. Oh, it looks a little mess here. So the second step is xk plus 1 minus equals xk plus 1 minus c lambda vk plus 1. So these two steps together, it gives us the hybrid proximal extra gradient method, okay? This is proposed by Soldov and Binar, also in 1990s, in another paper. Okay, this is algorithms. I will say it briefly. So you have the initial point, and you want to find a pair. Sorry, here they use the yk, vk, but they are the same. You want to find a pair. This pair satisfies either the exact proximal system or this inclusion, or this system with arrows in the operator and with arrows also in the system. So next step is the iteration. Okay, is the extra gradient step. And actually, this method converges. So first, we can have the phasor convergence of the whole sequence, which you can see the x is bounded and the yk minus ik is the distance of the yk and the xk is summable, and yk is also bounded. Okay, if we have some assumptions about this, here it's ck, which is lambda k in the blackboard, we can have some conclusion about the arrows. Okay, you can see here the arrows of the related to the operator could be summable. Okay, so we can have two conclusions. First is a global convergence. If we assume ck is greater than the c bar, which is strictly greater than 0, then the inclusion problem has solutions, and the xk converges to the solution. If the solution side is empty, if it has no solution, okay, then the sequence is unbounded. And we can also have the convergence rate. We just assume if the T inverse, the maximum monotone operator, the inverse of the maximum monotone operator is Lipschitz continuous and around the 0, then the sequence converges linearly, okay? And actually, it could not be faster than linear because of the extra gradient step. Okay, the hybrid proximal extra gradient method, HPE, has a lot of applications. One of the applications is by a paper in 2010 by Montello and Zweiter. They proved first the extra gradient method is a special case of HPE. Of course, you can see the exact extra gradient method is a special of HPE. You can also see the approximate extra gradient of approximate extra gradient method is also a special case of HPE. Okay, and they used the complexity theorem of HPE to study the complexity of the extra gradient method. This is somehow application of the HPE, okay, but we will not go deep in this paper. This is what we want to talk in the second slide, okay, the PPM, proximate point method, and the method of multipliers, and then the approximate point method. In one word, we have three kind of algorithms. First, by Rockefeller, which is the summable arrows, okay? And the second by Solodov and Binar, which only has arrows in the system with relative arrow criteria and with a projective step or projection type step. And the second is HPE. You have two arrows, one arrow in the operator, one arrow in the system, and also a relative arrow criteria. And last, you have extra gradient step. Okay, here are the reference. This first, it's the hybrid projection proximal point method. Okay, and the second, it's the HPE original HPE paper. Okay. And the third one is the enlargement of the monotone operators, okay? Actually, this kind of enlargement of monotone operators and also the theorem of monotone operators, they connect the maximum monotone operator and convex functions, okay? It enables us to use the knowledge from the convex functions to solve the problems for the problems related to the monotone operators, like inclusion problems, and you can see the inclusion problem with two operators in the next slide, okay? And also I use a lot of materials from the book by this Ernest and Watao-in, okay? From this book is a very, very, very nice book about the topic about the monotone operators and many algorithms, okay? And the very famous book, Convex Analysis and Monotone Operator Series by Bauschke and Combats. and also the very classic one, convex analysis by Rockefeller. Okay, this is all what I want to talk about in the second slide. Then we will go to the third one, about the splitting method and the splitting problems. Okay, so in the previous two slides, we talk about the problems with this form. The form which is an inclusion problem, but only have one operators here. In this slide, okay, we will concentrate on the problems, also which also is the inclusion problems related to the maximal monotone operators, but it's like a plus b of x, or even 0 belongs to the sum of k n, k equals to 1, a I x. Okay, it's inclusion problems with many operators. They are somehow similar, has some similar theoretical properties, but the algorithms for solving the inclusion problem with many operators are totally different from the method we have analysis before. Okay, so we will talk about three topics in different perspective. First, we talk about the back-forward or forward-back, this family splittings. Then we talk about the Douglas-Rachford family splitting method. Actually, the first and second classes, this kind of splittings, they are similar because they analysis from the solution side of the inclusion problem. But the third one, which I call it projection type splitting, which is different. This family of method is based on the fact that I have discussed here, that the PPM is it can be regarded as a projection method, okay? But PPM is just for one operator inclusion problems. Actually, it's possible to develop also projection method, but for solving the sum of two operators or even sum of m operators. Okay, the first question is, if we assume, okay, if we assume A and B are monotone, we first assume analyze the inclusion problem with two operators, okay? If we assume A, B are maximal monotone, and also we assume A plus B are still maximal and monotone. Be careful. If you have the first assumption, you cannot get the second automatically. You need some assumptions, okay? But even if we have this, these assumptions, when we have these assumptions, the sum of the operator is still a maximal monotone operator. The question is it still or possible or practical to use the PPM to solve these problems? If we use the PPM to solve these problems, what can we get? We get xk plus 1 equals to the resultant of A plus B of xk, okay? By the definition of the resultant, it equals to the identity plus lambda A plus B inverse. xk. The difference is in the approximate point method, we only need to solve this resultant only respect to A. But the difference is here is we need to solve or calculate the resolvent at the same time related to A and B. The point is you need to calculate them together. This is a point. Intuitively, this would be difficult or much more difficult than you calculate the resolvent of A and the resolvent of B independently. This will be much more difficult than you calculate them independently. We will give 2 examples to explain this kind of things, okay? The first one is not very proper, but I think it can still explain something. We consider about the convex feasibility problem, okay? We want to find the point which X belongs to the A intersect with B. And here, AB are convex and closed, okay? We assume the interior of the intersection is non-empty, okay? Which guarantees that the sum of the normal cone operators are maximum monotone. Okay, actually we have discussed before a normal cone operator here, NA or NB, are maximum monotone if A and B are closed and convex. This we have discussed before. But the normal cone of A plus NB will be still maximum monotone. It requires some assumption. So if we assume that the interior of A and B is non-empty, we can conclude that the sum of these 2 normal cone operators are still maximum monotone. Okay? So it is equivalent to solve these inclusion problems. Okay? If you solve these inclusion problems, you can solve the feasibility problem at the same time. So now we concentrate on these problems. We already said the sum is maximum monotone, okay? So we utilize ppm, which is equivalent to, sorry, it's the capital N, okay? It's a normal cone here. By the fact from this paper, we can know that the resolvent of the sum of normal cone operators is exactly the projection to A intersect with B, which means the ppm works like this. If you have a point xk, then you know you project to intersection of A and B. Actually, this is a little bit somehow not practical, because if you know the closed form of a point projects onto intersection A and B, it is not necessary to find a point anymore. You can calculate the projection directly and then you solve this problem immediately, okay? I will write it here. We want to solve this feasibility problem with the regularization condition that interior of is non-empty. Okay, so it is equivalent to say solve 0 belongs to the normal cone A plus normal cone of B of X. Okay, so this is a maximal monotone operator. Then we use ppm, which is xk plus 1 equals to, we use a resolvent, but Na plus Nb, okay? And we can know that the resolvent of it is just the projection of, sorry, we should xk here, okay? And we know the resolvent of this is just the projection of a point xk onto A intersection with B. If you know the closed formula of this, you can calculate it directly. You do not need to do the iterative, use the iterative algorithm to solve this problem, okay? The common situation is, to solve the problems, we usually have like the closed formula of projection to A, or somehow you can know how to calculate the projection to A. And independently, you can know how to use the how to calculate the projection to B. But usually you do not know how to projection to intersection A and B. Okay, so the common method is like you can use the composition of them, like PA composes PB, okay? And you can use the average of them, like 1/2 PA plus PB, okay? So somehow, if you use these two operators to solve the problems with fixed point iterations, for example, this you can get the map, which is called the alternating projection method, which is like xk plus 1 equals to the projection A, projection B, xk. And this you can get the simultaneous projection method, which is xk plus 1 equals to 1/2 PAXK plus PBXK, okay? This is an example of what we call the splitting method, because instead of calculate the resultant related to the sum of these variables, we can calculate the resultant. Actually, this PA is the resultant of the resultant of the normal cone operator NA, and this is the resultant of NB, okay? In these two algorithms, we use PA/PB independently or separately, which means we use the resultant of NA and NB separately. Not like here, we calculate the resultant together. This is the idea of splitting. We split the resultant of the original problem to smaller ones, to projection to A, projection to B. Okay, this is an example of why sometimes the PPM doesn't work very well, and what is the motivation of splitting method. Next, okay. Next example is the convex combination. Okay, we want to minimize the sum of x plus g, and both f and g are CCP function in the whole space. Okay, then the optimality of these problems is equivalent to solve this inclusion problem. Okay, this equivalent hold when the total duality holds, which means the primal problems and the dual problems has solutions, and the optimal value are same. Okay, so since the sum of two subgradients are still maximum monotone, we can use PPM to solve this inclusion problem. So it gives us this iteration. Okay, we calculate the resultant of partial f plus partial g, which is the proximal operator of partial f plus partial g, which is argument of this function. Actually, find the minimizer of this function, which is almost as the same difficult as solve the original problem. So the proximal point method didn't give us too much information for this kind of summation, minimize summation problems. Okay. So next we want to solve. We will introduce the splitting method. This is what we have discussed. We have mentioned before. Actually, we will introduce a little one more. Okay, the splitting method with more for more than two operators. One for the okay. So first we introduce this. idea of the operator splitting is we split the inclusion problems into smaller or simpler compositions. We calculate the resultant of A and B, not together, okay? Especially we transform the inclusion problems like this to a fixed point iteration or equation constructed by A, B, C and their resultant. Okay, we have three ways to design or construct this kind of splittings. First, we formulate the optimization problems or whatever the problems you are interested to monotone inclusion problems. Okay, then we apply a kind of splitting scheme, then we use the fixed point iteration with kind of scheme. First, let's say the forward-backward splitting. We consider this summation inclusion problems. We assume A, B are maximum monotone, and also A is single valued. Okay, we assume A is single valued. So we analyze from the zero side of these problems. Okay, if zero belongs, this inclusion is equivalent to this inclusion. Okay, this is trivial. Okay, and then we put this term on the left side. Okay, and then we get this inclusion, and then we use the definition of the resultant. Okay, we use the definition of the resultant. We get X is equals to the resultant of B times the identity minus LAX. Just take care. Just be careful. Here is the inclusion. Okay, because we do not know the I identity plus alpha B is a single valued or no. But here we can use equal because the resultant of a maximum monotone operator is single valued. Okay. So from the analysis here, we can conclude the 0 point of the summation A and B is equivalent to the fixed point of this operator, and this operator is what we called forward backward, because here we use A in the forward direction without inverse, and we use B with its resultant, it's the inverse. Okay, so it's the backward. So this is called, this operator, we call it the forward backward FBS. Okay, and if we use the fixed point iteration with the FBS to solve the inclusion problems, the question is, when will it converge? We need some other assumptions. Here, we need to assume that A is beta cocoercive. Why? If A is beta cocoercive, we have mentioned this kind of property before. This forward step, I minus identity minus alpha A is averaged. And of course, the resultant of B of a maximum monotone operator are still is averaged. Then the composition of two average operator is still average. This is why this iteration will converge, this xk will converge to the fixed point of the FBS. Okay. But we will see that if the composition of two not averaged but non-expensive operator, then the composition will not cannot guarantee the sorry, I will say it again. If here we calculate the composition of two firmly non-expensive operators, then the composition, we cannot guarantee the composition is still firmly non-expensive. But if it is averaged, then the composition will preserve the averageness, okay? Next, we will see application of the forward-backward splitting, okay, which is the Proximal gradient method. We go back to the minimization of the sum of two CCP function, okay, and we assume we have a furthermore we have additional assumptions that f is differentiable, okay, and then the minimizer of the f plus g is just the zero site of the gradient plus the subgradient of g or subdifferential of g. And here, this is if we want to solve this, if we want to solve this problem, it is equivalent to find a point in the zero site of this maximal monotone operator, okay? But here we want to use the FBIs, okay? We want to use the FBIs, okay? We regarded the gradient f as the operator A and the subgradient of g as the operator B. Then because f is a differential, then the subgradient becomes the gradient. Then it is single valued, okay? So the gradient of f is single valued. So first, we calculate the forward step, okay? The forward step is just the gradient descent step of f, okay? And then we calculate the resultant of the B, which now is the subgradient of G, okay? And I think I can write it here, it's better. So we want to the problem is minimize fx plus g such that x belongs to Rn. Okay, and here we assume that f, g, c, c, p, and f is differentiable. Then it is equivalent to solve. We want to find the 0 belongs to the gradient of f plus the subgradient of g. Okay, we regarded this as a operator A and this is a operator B, and this A and this subgradient is a single valued. Okay, it's a single valued. So we can use the forward-backward iteration. Okay, the FBS works like xk plus 1 equals to the resultant of b I minus lambda a xk, okay? So it's equivalent to the resultant of the subgradient of g I minus lambda a is the gradient of f xk. And recall that the subgradient of the resultant of the subgradient of a CCP function, it's just the proximal operator of the function g. Then we put x, we plug in x here. It is xk minus lambda subgradient. Okay, so this is the FBS, forward-backward splitting, for the minimization of the sum of two CCP functions. One of them is a differentiable, okay? And if the solution exists, if the L is smooth, okay, if we assume the L is smooth, and also the alpha belongs to 0, 2 over L, then we can have the convergence, okay? We can have the convergence. It is equivalent Okay, if we write the definition, we use the definition of the proximal operator here. We can recall what is the definition of the proximal operator. The proximal x g is equals to the argmin of g x plus 1 over 2 at point x, okay? At x minus y. This is y, okay? Square. This is the definition of the proximal operator. Then we can rewrite the FBIs in this form, okay? In this form, and it's at point xk. It has two parts here, okay? Actually, three parts. First is about the function f. It's a linear approximation of f at point xk, okay? And then the original function g, because g is, we do not assume g is differentiable. And then a penalty term, which guarantee the next point xk will not be very far away from xk. And if the function g in the problems here, if this function becomes the indicator function, it becomes the indicator function delta c of some convex closed set, okay? Then the proximal operator of g will become the projection. Sorry, here, it is a projection to c, and then this FBS becomes the projected gradient method for solving the constraint problem. If we want to minimize fx plus g here becomes, okay, it's g becomes the indicator function. Okay, it is equivalent to say we want to minimize fx such that x belongs to c, okay? So it is actually it becomes a constraint problems, okay? And by the analysis here, this is equivalent to solve 0 belongs to the gradient plus the subdifferential of an indicator function. It's the normal cone, okay? It's just the normal cone. Then we use the FBS, okay? We use FBS. It becomes xk plus 1 equals to the resolvent. This we regard it as B. This we regard it as A, okay? The resolvent of normal cone. And identity minus. And we know that the resolvent of normal cone is just the projection to C, and we plug in x, we have xk minus lambda, the gradient of f at xk. So this is just the projection gradient method, okay? It's a special case of forward, backward splitting. Okay, next we introduce another kind of splitting. It's called, it's inverse, okay? It's backward, forward splitting. The difference is just they perturb the order, okay? We also began from analyzing the solution side, okay? If 0 belongs to the summation of A and B, it is equivalent to say this, we have discussed before. Here, we define what? I will write in the blackboard. We began from 0 belongs to A plus B x 0, okay? It is equivalent to say that 0 belongs to identity identity plus lambda b minus identity minus lambda a, okay? So this is equivalent to say somehow the I minus alpha a x here, x okay. In the forward backward, what did we do? We just use the resolvent here. If this is single valued, okay. If this is single valued, we use the definition of the resolvent. We get the forward backward directly. But here, because here it's a different. The difference is we do not assume A is somehow single valued, okay. So we define this, we define Z equals to I minus alpha A X. Okay? It is one of the, I think I made a mistake. Then, yeah, okay. If we define Z equals to I plus, no, it is not correct. We need to define Z belongs to the I plus alpha B X, okay? Then, since it may has a lot of output, but Z is one of them, okay? Since Z is a vector, then we can rewrite this inclusion as an equation. So we have I minus alpha A X equals Z, okay? We have this equals Z. And from here, from this definition, we have what? We can calculate the resolvent, okay? Then we can have X equals to the resolvent of B, and then we can have, we expand it. No, we use this here. We have I plus alpha A resolvent lambda B this X equals to the resolvent of Z comes from this one. We define Z belongs to the output of this operator, and the input is X, and by the definition of the resolvent. And then, because Z is just one vector, so this inclusion because the equality, okay? And we use the X equals to the resolvent here, so this X becomes the resolvent of Z equals Z, okay? So it is equivalent. Began from 0, the solution side of the summation, we have a fixed point, okay? And the operator is here. This is the operator of the fixed point, okay? So it's a little different. It's a little different from before because the sequence here somehow is zk, okay? And if we use the sequence here, and if we use the fixed point iteration with respect to this operator, then we may have zk converge to z star. But Z star is not a solution of the original inclusion problems. So if Zk converts to Z star, what is the solution? The solution should be X star equals to the resolvent of B at Z star, okay? So this backward, this is called a backward forward, okay? Because we use this resolvent first, and the operator A itself later. So we call it B backward F S, backward forward splitting. The difference is the sequence is different. The sequence will not convert to the solution for the original problem directly. After you get the limit point of this fixed point iteration, okay, and then you take one more resolvent again. Okay, so you see here, if X belongs to the zero side of A and B, X is a solution, okay, then it is equivalent to Z is a fixed point of this iteration or this operator. And also the relation between X and Z is you need to do one more resolvent here. So this is called backward and forward splitting. And the fixed point of the backward forward splitting is like this. We represent it in the two lines scheme. The first line is, if we have a point zk, first we calculate the resolvent, then we get the xk, and in the second step we take the evaluation of operator A, and then we together with this xk plus 1 we get the next zk plus 1. Okay, and the assumption of the convergence is also we need to assume A is concursive and beta belongs to 0 to 2 times beta, and then we also need to assume that the solution side is non-empty. This is somehow backward forward splitting. As assumption, okay, BFS and FBS, this is xk plus 1 equals to first backward, okay, and first backward forward. We make a summary. In these two splittings, we use 1 times of resolvent, okay, for B. And another operator, we didn't use the resolvent. We use the operator directly, okay? We use operator directly since we assume they are single-valued. Since you are single-valued, you can use the operator directly. But since you use it directly, if you want to guarantee the convergence, you need somehow more assumptions about this operator. For example, the concurrency of A, okay, concursive. The next question is, if we use the resolvent not only for B but also for A, the good point is, if we use the resolvent of A, we do not need to assume A is a single valued, right? Here, for this operator, if you want to make the algorithms clear, or somehow you want to determine it very easily, usually you need to assume it is single valued here. It is single valued. But if you use two resolvations or composition of two resolvent, you will not have this kind of confusion or furthermore assumptions. Okay, but first let's analyze whether this will converge. The resolvent of B is averaged, or is 1 over 2 averaged, okay? And the resolvent of A also is 1 over 2 averaged. The composition of these two averaged operator is still averaged, okay? So we can conclude that this iteration will converge, but the problem is it will not converge to the solution of A plus B, or the zero side of A plus B, okay? Actually, the fixed point of the composition of two resolvent consists of the solution of this following simultaneous inclusion problems, okay? It's the fixed point side is actually the solution of these two inclusion problems. But these algorithms, double backward algorithms, is still useful. It could be solved. What kind of problems? Instead of solving 0 belongs to A plus B of X, the zero side of summation, we can solve the common 0 point of A and B, okay? The common of A minus and A inverse and B inverse, okay? And if A and B are the subgradient of two CCP function, then the double backward method or double backward splitting can solve the fixed point of this double backward splitting are corresponding to the minimizer of this function. This is somehow the applications of the double backward method. Next, we will introduce the Douglas-Rachford family splitting. I will write the double backward splitting here. It is xk plus 1 equals to the resolvent of A composition with resolvent of B xk. In these three different splittings, we use the operator directly or the resolvent. Let's recall that in the first class or in the first slide, we have defined another operator. We call it Cayley operator or reflection operator, which we can write R lambda A, which is 2 times the resolvent of A minus the identity, okay? It's the reflection operator. All of this splitting doesn't use the reflection, only the resolvent itself. But what will the algorithms looks like, or it will converge? If it converge, will it converge to the solution if we use the reflection instead of the resolvent? The Douglas-Rachford family splitting will answer this question. Okay. We still consider about these inclusion problems of the summation of two maximal monotone operators. Okay, this family splitting can be represented in the following way. Okay, actually, it's kind of a convex combination. It's a kind of combination or over-under relaxation. First, we have this red part. It's actually the reflection of A composition with reflection of B. And then you make a combination with identity. Okay? And this system, oh no, not system, this iteration or splitting converges when A and B are maximal monotone. And this coefficient rho k is greater than 0 and less than 2, and the solution set is non-empty. We state the convergence result in the beginning. Okay, so what is the Douglas-Rachford method? If beta k equals 1, this is called Douglas-Rachford. If beta k equals to 2, this is called Pisman-Rachford splitting. Actually, you see the assumption for the convergence here about the beta k, it should be less than 2. So we can guess if beta k equals to 2, which is the Pisman-Rachford splitting, it may not converge by the result here. Okay? First, we analyze the Pisman splitting. Okay? We need to recall a fact, which is that if A is maximal monotone, then the I minus alpha the identity minus alpha A is equivalent to the composition of I plus alpha A, composition with the reflection of A. Okay, this is the proof of this identity is not difficult. You just use the definition of the resolvent. It's enough, and we do not need further more assumptions about A. Okay, and okay, let's begin here. Actually, I want to see in advance, even if this Pisman-Rachford method of splitting cannot guarantee the convergence, but the analysis of this method is still very useful because it has a relationship with, it has connections with the Douglas-Rachford. That's why we analyze the Pisman-Rachford splitting here. Okay. So first, we can do it in the blackboard. First, we begin from the solution side. 0 belongs to A plus B identity, which is equivalent to 0 belongs to I plus alpha B. I use B or A. Okay, I use A here. And minus I minus alpha B here. Okay, and this is X, and we have X here, we have X here, and then we keep this part the same, but we use a fact for this part. Okay, this will equals to the resolvent of B and I plus lambda B X. Okay, and then we can define a vector Z belongs to I plus I lambda B X. Okay, so by the definition of resolvent, this is also, this inclusion says X equals to the resolvent of B at point Z. Okay, so we use this equality in this inclusion, then we get this is still equivalent to 0 belongs to identity plus alpha A, X equals to the resolvent of B, Z, and minus the reflection a reflection of B, I plus lambda B, this X equals to the resolvent, okay, the resolvent of they. Okay, and by the definition, this is somehow, because the resolvent is just I plus lambda B inverse, okay? So this is equivalent to, I still write it here, is equivalent to 0 belongs to I plus alpha A, the resolvent of they, minus reflection B of they. Okay, so we have this result, okay? And we need to say, in this inclusion, we do not need there is not X anymore. This inclusion is related to the variable z, okay? Z is the relation of X and Z is defined by this equality. So we put the resolvent on the other side. We put the resolvent on the other side. We have, it is equivalent to say, I think first we expanded this, because this is equals to 2 resolvent of B minus I, the definition of the reflection. So it is equivalent to say 0 belongs to I plus lambda A, okay, and the resolvent of B, Z, and we expanded this minus 2 resolvent of B, Z, plus Z. Okay, we get this, and we get this one. And we put this term on the other side. It is equivalent to say Z belongs to 2 resolvent, we put Z on the other side, okay? Z plus I plus lambda A, the resolvent of B, okay? But we still have I plus alpha A here. We need to eliminate this term. Let me see. Where should we limit this term? If we take the resolvent on the both sides, 0 belongs to of Z belongs to I plus lambda of A, resolvent of B of Z. And then we use the definition of the resolvent, okay? So then we see that the resolvent of B Z is equals to the resolvent of A and times 2 reflection of B Z. Okay, we have this. I just put this term on the left side, and we have this equivalent inclusion. And then we use the definition of the resolvent of A. So we have this term. So we have this term, okay? And but where is the okay? We use the definition of the reflection here. I write the definition of reflection here. The reflection of B equals to 2 times of the resolvent of B minus I. Then we can have the resolvent of B equals to 1 over 2 reflection of B minus 1 over 2 identity. So here we have this resolvent of Z can be equals to 1 over 2 reflection of B Z and minus 2. Where is this 2? Okay, 2 is there, okay. This is 1 over 2 identity of Z. It's Z belongs to the resolvent of A times 2 resolvent of Z. So we have resolvent B of Z minus Z equals to the resolvent of A to reflection of BZ. Okay? And then we put Z on the other, we put Z on the one side, and it's equals to it is equals to, sorry, we have 2 here. It is 2 reflection of B Z minus 2 the resolvent of B 2 reflection of B Z. There is a problem. Where is A? Okay, here. This is A. This is A. Okay, we already have this. But we have something wrong here. Okay. And 0 belongs to, okay. This is Z. X becomes the resolvent of A, resolvent I plus B, resolvent, okay. So this is the identity plus I, resolvent of B, minus reflection of B. Okay, then we have sorry, this should be all equality. So we have reflection. This should be reflection of BZ equals to reflection of BZ equals to identity plus I minus resultant of A, and these two, or we can write it as a definition, or we can write it here. So the resultant of BZ is equals to the resultant of A to reflection of B day. The resultant of A reflection of B is equals to, okay, but where does this 2 comes from? Where does this 2 comes from? Okay, sorry. We still use the reflection here, okay? Reflection here. So it's minus the reflection of B, Z. So this is also equality because of definition here. And then it is equivalent to this. We put it on the other side. Then we by the definition, it is by the definition of the reflection. By the definition of the resultant, we have this one. Okay. And we do not have 2 here. We do not have 2 here. We do not have 2 here. Okay. So we put Z on one side. Another side is reflection of Z minus. Okay. Okay. And this is equivalent to reflection of BZ minus 2. We use, it is equal. We use that the resultant of A equals to 1 over 2 reflection of A minus identity here. So it becomes the reflection. This becomes the not 2 times 1 over 2 reflection of A minus identity. Composition with this. Okay, we use the definition of reflection here. So Z equals to the reflection of BZ minus. So this is 1 here, and the first part is reflection of A, composition with reflection of B of Z, and the second part is plus the resultant of B Z. There should be some minus 1. They equals to sorry. This is plus. So this is minus. So they are equal. Okay, then we have Z equals to the reflection of A and then reflection of B and z. Okay, so from here we know this z belongs to the fixed point of reflection A and the reflection of B, the composition, okay? And be careful, here is a point Z, okay? This is a fixed, somehow you can use this operator as a fixed point iteration with respect to point Z. But we have a definition here, we have a definition X here. So X can be defined by the resolvent of B at point Z. Okay, so this is a relation. From the beginning, from here, we have a point Z, X. Actually, this means X belongs to the zeroth side of A plus B. Okay, we have a zero of A plus B. Then we have a lot of equivalent statement. Then finally we have a point Z, which Z is a fixed point of this operator. So we can make this conclusion. Sorry about the late. I will finish very soon. So we conclude that the X, if X belongs to a 0 point of side, then it is equivalent to say Z is a fixed point, and also this relation. Then this is the Peaceman-Rachford method, splitting method, okay, splitting method by this operator. If this zk converges to a z star, if we use zk plus 1 equals to RB, no, RA, RB, XK. This is Peaceman-Rachford iteration. If zk converge to some point z star, and then we calculate x star equals to the resolvent of z star, then this x star is what we want. The z belongs to the 0 of A plus B. Okay, but the problem is, can you guarantee this zk converts to z star? Because of the property of this composition of these two reflections. We will continue in the next class from this page and introduce the Douglas-Rachford method and the application of Douglas-Rachford method and a more concrete example of lasso problems and the history of the DRM, okay, the Douglas-Rachford method, okay, the convergence of the DRM is not very easy to get until 2011, okay, and then we will also prove that actually the Douglas-Rachford method is a special case of proximal point method, and then we can also from this slide we will prove that the EDMM is also a special case of the Douglas-Rachford method. Okay, we will stop here.